Yeah, thank you, Manuel. Thank you also for the opportunity to present this talk at this very nice seminar, and very useful seminar. So this talk is based on a on joint research with Dario Valdebenito. Okay, so we'll be talking today about semilinear elliptic equations of the following form. They are on the entire space in dimensions 3 at least. Okay, so the space is Rn plus 1 and at least 2, and the nonlinearity in the equation is of class C1 at least, and it vanishes at the origin and has negative derivative at the origin. So that's the structure of the equation for the whole talk. Okay, so these two conditions mean that we have a constant solution without loss of generality put at the origin. And the derivative being negative means, for example, from the point of the corresponding parabolic equation, that the trivial equilibrium is asymptotically stable as a steady state for the parabolic equation. Okay, so that's a situation one often wants to study. For example, interesting questions are how propagation happens about the stable equilibrium. Now, in other settings, this condition also appears naturally, for example, in the Schrödinger equation, when one looks for a standing wave solution. So that would be a solution with separated variables, u depending on x only, and then the exponential depending on t. So such a function is a solution of the Schrödinger equation if the function u solves the equation Laplacian u plus u to the p minus lambda u. Okay, so if lambda is positive, we get an equation of the form considered. Now, for Schrödinger equation and other dispersive equations, perhaps the relevant solutions are finite energy solutions, and those would be solutions decaying to zero at infinity in all variables, so fully localized solutions. But for parabolic equation, for example, other solutions are also relevant. If we take the parabolic, so we consider the parabolic solutions of the parabolic equation with non-negative initial data, the solutions will stay non-negative for all times, and therefore non-negative solutions of the elliptic equations are relevant as steady states. And even though we may start with an initial condition which is fully localized, there is no reason for the solution to stay localized. So equilibria which are not decaying in all variables are also relevant for this equation. Okay, so in this lecture, I will specifically look at solutions which are partially localized. They decay in some variables, but not all of them. Okay, so partially localized positive solutions. Now, for the sake of background, let me briefly mention some classical results concerning fully localized solutions, to which I refer as ground states. Okay, so in this talk, a ground state of the elliptic equation simply means a positive solution which decays to zero at infinity. There's nothing to do with energy here, just decay. Even though such ground states are finite energy solutions, because the decay is exponential due to the condition on the derivative of f. Okay, so by classical results, the classical result of Kidasen and Nirenberg, we know that all such solutions are radially symmetric around some center. And there have been many studies. One of the early systematic studies of existence, non-existence results are the two papers of Beresticki and Lyons, and many other after that. Many people have also found conditions for the uniqueness of the solution up to translation, okay, uniqueness of the ground state. So for example, for the power nonlinearity, Kwong proved that we always have uniqueness when we have existence, and we do have existence for the exponent p subcritical, Sobolev subcritical in dimension n+1. Right? n+1 is the dimension of the space where we consider the equation. Okay, so these are well understood, fully localized solutions. Now, when we don't make any decay assumption on the solutions, we get a vast variety of solutions. So I put here some references without trying to be exhaustive. But the point is, I think it's a fair statement with which the experts in the audience, the organizers, for example, would agree that without any decay conditions, the structure is way too complicated to be amenable to any classification or general description. Okay, so what I will do in this, what I'm trying to do in this lecture, and we did with Dario in our research, is to consider solutions between the general solutions and fully localized solutions, partially localized solutions. Okay, so we have a better chance to understand this smaller class of solutions. Okay, so among solutions which are partially localized, positive, perhaps the most interesting case is the solutions which decay in all but one variable. Okay, so from now on, I'll consider the equation in the form where the Laplacian is the Laplacian with respect to x, the first n variables, and I single out the last variable and call it y. Okay, so we have the solutions decaying in x uniformly with respect to y and positive are perhaps the most interesting partially localized solutions. But also I will briefly talk about solutions which have other predetermined behavior in the variables x, like the solutions which decay in the first n-1 variables, are periodic in the nth variable, and no specific behavior imposed in the last variable y. Okay, so the question about such types of solutions is what kind of behavior can we expect in y, in the last variable. So the behavior in x is predetermined, no complexities there, just the behavior in y is still open. So if there are any complexities in such solutions, they would have to be due to the behavior in y. Okay, so that's the key issue. What kind of behavior in y we can expect? Now let me mention also that so there is a remark concerning the behavior in x. Although it is predetermined by the decay or periodicity, one interesting question is whether the solutions, positive solutions, have to be radially symmetric in the decay variables, x or x prime. Okay, so this is something we would expect in view of those Gidasny-Nirenberg type results for fully localized solutions. And this has not been proved in the full generality yet for partially localized solutions, although there are nice, rather general results in that direction. Busca-Pelmer, sorry, Patrizio, for misspelling the name. It's Patrizio Pelmer, Gui, Malchiodi, Shu, and the last paper I know of is Paria, Malchiodi, and Rizzi. All right, so what kind of partially localized solutions are known to exist? So let's talk for now about the solutions that decay in all variables x. Okay, so this condition D, full decay in x, no imposed behavior in y. Okay, so trivially we get an example of such solution, which is not fully localized. Namely, we take a ground state in Rn, if it exists, one less dimension, and view it as a solution on Rn plus 1 constant in the last variable y. All right, so that's a trivial example. Now for, there are, this is not very interesting, of course, but there are also solutions which are non-constant in y and not decaying in y. Dancer, Malchiodi, Alessio Montechiari studied solutions which are periodic and non-constant in y for a large class of nonlinearities, including in particular the power nonlinearity with p subcritical in dimension n. Okay, so such solutions are known to exist. Now, it's not difficult to prove the existence of periodic non-constant solutions, but in these papers, much more has been done. Okay, so the authors studied qualitative properties of such solutions as well as some global structure of such solutions. For example, Alessio Montechiari is a very nice study of global branch of periodic solutions and how it fits the mountain pass structure of the problem. Okay, so periodic solutions exist. What else? Are there any other solutions of this problem D? And in the paper of Gu, Malchiodi, and Shu, this question is asked in an even more specific way. Are all solutions of D periodic in Y? Okay, and while this is certainly not true in general, as we will see in a moment, for the power nonlinearity, this is a very interesting question, not yet resolved. Okay, and I will make some comments about that later. Jumped back somehow. Okay, so we'll be looking for different sort of solutions, namely quasi-periodic solutions. Okay, so the question I will address in this talk is, do quasi-periodic solutions exist? And you will see in a moment that the equation has a Hamiltonian structure. Actually, there's a formal Hamiltonian structure as well as a rigorous one. And this makes this question a very natural one. Okay, and it is also a meaningful question to ask for the general class of equations. Okay, do quasi-periodic solutions exist at all in this kind of equations? And it makes sense to ask this question for more specific nonlinearities like the power nonlinearity or combined powers, which has been studied a lot recently. Okay, let me recall the definition of a quasi-periodic solution first of all. Okay, so that's the quasi-periodicity in Y. Okay, so what it means is that when we consider U as a function of Y, taking values in the functional space, functions of X, for example, a Sobolev space, and Y is a real variable, then this function can be written in terms of an embedding of an n-dimensional torus in the functional space. Dimension n is at least 2. In the following way, it's the composition of the embedding phi with this linear map where we simply multiply y by numbers omega 1 to omega n, which are assumed to be rationally independent. okay, non-resonant. They are called the frequencies of the quasi-periodic solution U. Okay, so what this means in particular is that when we view the image of this function of y in the functional space, okay, so the trajectory, so to speak, of u, this image is dense in the torus, and the torus has dimension at least 2. Okay, so in particular, the solution is not periodic in y. So this is entailed by the definition where we require the frequencies to be rationally independent. Okay, so these will be different solutions than the periodic solutions known previously. All right, so let me also recall how quasi-periodic solutions and why they are naturally expected to occur in a Hamiltonian system. So I recall a basic KAM type result. Okay. So consider a Hamiltonian system in R2n, so n degrees of freedom. And it is written in the following way. The coordinates are I and theta. Theta is in the torus. So everything is periodic in the variables theta, period 2 pi, say. And I is in an open set in Rn. The Hamiltonian for this system, H, is assumed to be written as the sum of an integrable Hamiltonian, which only depends on I, and a small perturbation. Now, this is the structure you can find, for example, when you take a Hamiltonian system with an elliptic equilibrium. Okay, elliptic means that all the eigenvalues of the linearization are on the imaginary axis. And if those eigenvalues are non-resonant to a high enough order, then you obtain this structure in action angle variables. Okay, the Hamiltonian, which is integrable, comes from the Birkhoff normal form up to a high degree, and the rest is high order terms, which can be considered small. Okay, so this often happens near an equilibrium. And if the equilibrium is not completely elliptic, meaning there are other eigenvalues, you restrict it to the center manifold, and you obtain this situation on the center manifold, reduction to the center manifold. Right, so now the flow of the unperturbed integrable Hamiltonian is very easy to understand because the derivative with respect to theta is 0, the gradient with respect to theta is 0, so I stays put, it's constant in time. And then we have the dynamics on the corresponding torus. Okay, so the whole state space is covered by invariant tori in this integrable system. And on each of the tori, we have the rational flow given by this constant vector. Okay, so if some non-degeneracy condition is satisfied, then most of these tori will carry quasi-periodic solutions, dense in the tori. Okay, so now the KAM Kolmogorov-Arnold-Moser type results can be used to prove that after a small perturbation, if some non-degeneracy condition on the integrable part is assumed, many invariant tori still exist after the perturbation. Okay, the ones on which the frequencies are not just non-resonant, but Diophantine, those will persist. So for the perturb, for the pool system, we get many, uncountably many quasi-periodic solutions. Okay? Many invariant tori with quasi-periodic solutions on them. Okay, so there are several different non-degeneracy conditions. One can use the classical one, Kolmogorov's condition, requires the Hessian of H0 to be non-singular. throughout some open set U. Okay, so these are classical results in the ODEs, in Hamiltonian ODEs. They have been extended to Hamiltonian's PDEs, like the nonlinear wave equation, Schrödinger equation, okay, which have a Hamiltonian structure, not just formal, but true Hamiltonian structure. Now, our equation, okay, so which we can consider in a more general form, this elliptic equation is similar to the wave equation. Of course, the sign, one sign is different. And they do have, like the wave equation, they have a Hamiltonian structure. Okay, but when we view y as time, the initial value problem for the second order equation is not well posed. Okay, so that's why I call it a formal Hamiltonian structure. So let me tell you more about that. Okay, so consider again the elliptic equation where the nonlinearity is allowed to depend on x, okay, not on y, but on x. And formally, you will view y as time. So let's write the equation as a first order equation, as a first order system in y. Okay, so your y is v, v sub y is what's in the equation minus Laplacian in x minus g. And now we see we introduce this functional on the space of functions of x. Okay, so Hamiltonian on functions u and v of x only. Right, so the right-hand side in the system can be viewed as a Hamiltonian vector field, so to speak, of this functional h. Capital G is the primitive of small g. Right, so you see, the first component can be viewed as the gradient with respect to v, L2 gradient of this functional h, and the second component would be a negative L2 gradient with respect to u of this functional, right? The usual, without v, this would be a kind of usual energy functional. So in this sense, the system can be viewed formally as a Hamiltonian system with this functional h. Now, this formal Hamiltonian structure is already quite useful, and it has been exploited in these papers. I mentioned two of them in the context of symmetry before, Busca-Felme. This time I got the name right. Alessio Montechiari, Gui Malchiodi-Shu, they used, among other things, the fact that this functional is constant along solutions of this system. Okay, we view them as function of y, taking values in a functional space, functions of x. It's constant, independent of y. So that's already quite useful, but that's not what we'll really use. Instead, we use a rigorous, so not just formal Hamiltonian structure of this equation on the center manifolds. Okay, so this is using something which is called spatial dynamics of elliptic equations. And this idea, originally due to Kirgesner, then developed by Casina Mora, Sola Morales, Milke, Schiele, Schorle, and used by many other people later on. So the idea is that even though the initial value problem for the original system on the infinite dimensional space is ill-posed, one can find finite dimensional manifolds which contain many solutions of the original PDE. Okay. Now, on those manifolds, we can consider a reduced system, which is an ODE, a well-posed ODE with well-posed initial value problem. And solutions of this ODE give us solutions of the original PDE. Okay, so that was the idea of Kirchner. First, in most of these papers, it's used on cylindrical domains with a bounded cross-section. We use such type of results for the full space, which also can be viewed as a cylindrical domain, right? Rn cross R, unbounded cross-section in this case, right? And another important fact about some classes of elliptic equations is that when you consider the reduction of the equation to the center manifold, it is truly Hamiltonian. It is a Hamiltonian system with respect to the reduction of this formal Hamiltonian to the center manifold, and with respect to some symplectic structure on the center manifold, which is not known explicitly, but it's known to be there. Okay, so it's a truly Hamiltonian system, and this is coming from general results of Milke. Now we also did computations specific to the equation, which also give us some additional information. Okay, so this is what we will be using, what we have been using for constructing, for finding quasi-periodic solutions. Now, there are other ways, even for ill-posed initial value problems like this equation, for constructing quasi-periodic solutions. So there are papers by Schorle and Bals for elliptic equations on a strip. Schorle has a different method. He does not use the reduction to the center manifold. And likewise, a very general paper of Della Labe and Sil on abstract analytic PDEs applied to Boussinesq's equation in particular, which does not use the reduction directly. They build a KAN theory for such equations in a very general analytic setting. All right, so more specifically about the setup, we need about the center manifold and what the center manifold gives us. Okay, so let's take the equation. Let's take the equation in this more general form for now with X dependence. And let's take a solution which is independent of Y. So without loss of generality, we can assume that it's a 0. So we have this trivial solution. And let's expand the nonlinearity at that solution. Formally, the solution 0 can be viewed as an equilibrium of this system, right? Where again, formally for now, we view Y as time. Okay, so let's take the linearization at the origin plus higher order terms in the system, and we need to involve the terms up to order 3 explicitly in this expansion. Okay, so we make now assumptions on the linear part. So the assumption on this Schrödinger operator, 2 of them, spectral assumptions. So first of all, we need the essential spectrum to be on the positive semi-axis, real semi-axis, away from 0. And this is guaranteed if the potential is negative near infinity. Okay, so that's a first assumption. And then we need at least 2 eigenvalues of this operator which are negative. So we assume that the spectrum in the negative semi-axis consists of simple eigenvalues, all strictly negative. Okay, so these 2 assumptions. So now what does this mean for the system, for the vector linear operator, the linear part of the system? Okay, so for this operator, the square roots of the negative eigenvalues give us n pairs of eigenvalues on the imaginary axis. Okay, simple eigenvalues on the imaginary axis, and the rest of the spectrum is away from the imaginary axis. Okay, so that's what we get for the system. A simple computation shows how the spectrum of this vector operator is related to the spectrum of the Schrödinger operator in the second component. Okay, so this is the right setup for the center manifold. The linearization has a spectrum on the imaginary axis, the rest of the spectrum away from the imaginary axis. So the existence of a center manifold together with the reduced equation can be proved. And the reduced equation has the following properties. Okay, so the reduced equation is an ODE on a finite dimensional space in a neighborhood of the origin in R2n. See, we have 2n eigenvalues on the imaginary axis, right? That's why we have a 2n dimensional center manifold. They are simple eigenvalues. The equilibrium so 0 is an equilibrium for this reduced ODE, and it is elliptic, an elliptic equilibrium, meaning that the eigenvalues of the linearization are precisely these eigenvalues on the imaginary axis. Now, this reduced equation gives us solutions of the original PDE, namely all solutions of this reduced equation which stay near the origin for all times actually represent solutions of the original PDE. So, of the system S, and therefore the original PDE. And the reduction, as I said, is a Hamiltonian system with respect to some symplectic form on R2n. Okay, so this is what we get from the center manifold. We get a Hamiltonian system on some finite dimensional space. Now we perform several transformations of the system. We use a Darboux transformation, which changes the symplectic form to the standard one. Then, assuming the eigenvalues on the imaginary axis are non-resonant to a sufficiently high order, we use the Birkhoff normal form to obtain an integrable Hamiltonian of plus a small perturbation. And finally, we use action angle variables. So after these transformation, the Hamiltonian system, the reduced Hamiltonian system, will have exactly the form which I showed to you before, right? The form which is suitable for an application of a KAM theorem if a non-degeneracy condition on H0 is satisfied. Okay, so we know that this can be done. These transformations can be done in general. We obtain a system of this form. However, this would not be any useful unless we could, at the end, obtain some conditions on the original coefficients, the coefficients in the original PDE, for the existence of quasi-periodic solutions. Okay, so we do all these computations, transformations carefully, keeping track of how the coefficients A1, A2, A3 appear in the Hamiltonian as it gets transformed by this transformation. And at the end, we indeed obtain conditions on the coefficients A1, A2, A3, which guarantee the existence of quasi-periodic solutions of the elliptic equation with n frequencies. Okay, n is the number of these negative eigenvalues mu1, mu2, and so on. Right, so the conditions involve eigenvalues. Okay. For example, we need the non-resonance condition. And they involve, again, functions of the Schrödinger operator and the functions A2, A3. Okay, so the conditions depend on A1 through the eigenvalues, eigenvectors, and also there are some integral expressions, like for example, for Kolmogorov's non-degeneracy condition, if A2 is not too big, we require the determinant of a certain matrix to be non-zero, where the eigenfunctions corresponding to the eigenvalues, to the negative eigenvalues, appear together with the function A3. Okay, so we have now sufficient conditions, and it's easy to construct examples of such functions which satisfy all the requirements, right? We can perturb them independently of each other. So we can, for example, make this determinant non-zero by choosing A3 generically for most A3. This would be satisfied if the eigenfunctions behave nicely in some sense. Okay, but so it's not difficult to construct to give examples of nonlinearities of this form to which the general results apply. Okay, but now we want to use that general scheme for solutions which are of a specific form, okay, the homogeneous equation with the nonlinearity satisfying the given conditions. So to do that, we use the linearization and expansion of the nonlinearity at a ground state in Rn. Okay, taking the linearization at a constant, like 0, wouldn't give us anything, wouldn't give us the required. Something strange is going on here. Can you see my screen still? Yeah, or...
yes, we can.
Yeah, okay, thanks. Linearization at 0 would not give us the needed spectral structure. Okay, so we take an expansion at the ground state, independent of y. So it's a ground state in dimension n. Okay, so take the linearization at the ground state, and then the second and third derivative, so the Taylor expansion up to order 3. So this gives us an equation in the form considered before. So now let's see if we can make those assumptions satisfied in this setting. So first of all, the first prerequisite is that the Schrödinger operator in this equation, namely the linearization at the ground state plus the Laplacian, has n negative eigenvalues, n greater than 1. Okay, so the ground state must have Morse index at least 2. That's the first requirement. So fortunately, there are examples of nonlinearities that give us such ground state. Dancer's paper or paper of Davila, Del Pino, Guerra. My paper gives such nonlinearities. Okay, so there are examples of nonlinearities, but it's not possible for all nonlinearities. For example, it's not possible to have such a ground state for the power nonlinearity. Okay, so now the second requirement was the non-degeneracy condition on these functions, A1, A2, A3. And this is a highly non-trivial issue. It's a major hurdle in this problem, because you see these three functions cannot be perturbed independently of one another, because they are all linked through the function f and the ground state, phi. Okay, so we perturb f, and the ground state, they change simultaneously. So it's a highly non-trivial issue, but we have done it with 2 frequencies. Okay, so we have the following theorem, which says essentially that equations of the considered form do have quasi-periodic solutions with two frequencies for some nonlinearities. Okay, so the nonlinearity is cooked up in that result, but it has the needed structure and it's smooth. Okay, so that's a result from several years ago. It appeared this year, but we proved it about 3 years ago. And we have worked on it recently, making some progress. So here is a more recent work. And we use a slightly different approach. We are working here with Hamiltonians with external parameters, building on results of Schorle and Brouwer-Huytema-Takens in ODEs, Hamiltonian ODEs. So we have the following improvements. Okay, so first of all, we have removed the restriction. The number of frequencies of quasi-periodic solutions can be arbitrary. Also, we have some somewhat explicit conditions for the existence of quasi-periodic solutions. So one of the results tells us that the existence of a ground state of Morse index greater than 1 is in some sense a guarantee of the existence of quasi-periodic solutions. Maybe not necessarily for the original equation, but for an arbitrarily small perturbation. Okay, so if the equation on Rn has a ground state of Morse index greater than 1, then for an arbitrarily small perturbation of the nonlinearity, the equation with the y dependence will have a quasi-periodic solution decaying in X with n frequencies. Okay, so this result, for example, can be applied in the nonlinearities with mixed powers, because this is precisely the nonlinearity for suitable exponent and lambda, coefficient lambda, considered in this paper by Davila, Delpino, Guerra, who proved that ground states with Morse index 2 exist. Okay, so small perturbations of such nonlinearities, arbitrarily small, give us quasi-periodic solutions for this problem on Rn plus 1. Now, we also have results which can be used for specific families of nonlinearities, such as this combined powers, without needing a perturbation. Okay, so directly in those families, under some conditions, one can find quasi-periodic solutions. Okay, so what we need in this case is that there is a family of ground state. So we consider the equation with a real parameter and sufficiently smooth nonlinearities. And if we can find a family of ground states of Morse index 2, bifurcating of a non-degenerate, of a degenerate ground state of Morse index 1, then without any perturbation for some lambda, the equation on Rn will have quasi-periodic positive solutions. Okay, so and this seems to be the case in the combined powers nonlinearity. They strongly suggested by the same paper, Davila, Delpino, Guerra, although it's not proved that, right? So there is a bifurcation diagram, partly numerical, which strongly suggests that this is what happens in this equation. I mean, most of their results are rigorous, of course, but they have some numerical bifurcation diagrams. So if they are confirmed, we would get quasi-periodic solutions directly in this type of nonlinearities. Okay, so finally, this is my last transparency. Let's consider the power nonlinearity. Okay, so we took the p minus u, p greater than 1. Okay, so the previous results do not apply. And so we can't, using those results, find quasi-periodic solutions in Y which decay in X. Okay, and the reason for that the prerequisite is never satisfied. We can't find a ground state on Rn with Morse index 1. It always, if it exists, for P subcritical in dimension n, it exists, but it always has Morse index equal to 1. Okay, so what we can do for power nonlinearity is the following. So we consider here the other class of solutions with predetermined behavior in X. Okay, but this time it's solutions which decay in X prime, the first n-1 variables, and are periodic in Xn. Okay, so in this class of solutions, we are able to find quasi-periodic solutions in Y. Okay, so if P is less than the Sobolev exponent in dimension n-1 and is an integer or sufficiently large, we need a high degree of smoothness of this nonlinearity. Okay, so if these conditions are satisfied, then a quasi-periodic solution satisfying these conditions, PD, exist. Okay, and we can use the machinery which I discussed before in the following way. We take now a ground state in dimension Rn-1, so the radial, the unique radial ground state for this equation. View it as a solution on Rn, which is constant in Xn. In particular, it's periodic in Xn with any period. And if you choose the period suitably, this solution will have Morse index 2 in the space of functions decaying in X prime and periodic in Xn. Okay, so we can use our general results and apply it in this equation. Okay, so finally, final remarks. Coming back to the solutions which are decaying in X, in all X variables, and so the solutions which are which satisfy the condition for the power nonlinearity can exist only if P is Sobolev subcritical in dimension n. That's what was proved by Gui, Malchiodi, and Schuh. Okay, so in this region, the existence of quasi-periodic is open, but I think the following conjecture is rather safe. So this should be true. Quasi-periodic solutions exist for P between the critical exponents in dimension n and n+1. Okay, so I'm not afraid to make this conjecture. I'm not so brave to make a conjecture in the remaining range when P is less than n+3 over n-1. So this is open, but I don't see any indication of the existence of quasi-periodic solution. So it may well be true that we have a Liouville theorem in this case, namely all solutions satisfying D, so this decay condition in all variables X, are contained in the global families of periodic solutions found by Dancer and Alessio Montechiari, and their asymptotic limits, the limits of these global families, which are ground states in dimensions Rn on one side and Rn+1 on the other. All right, I see I'm 2 minutes over time. Sorry about that, but thank you everybody for your attention.